Hello, good afternoon, everyone. So today it's really nice to have Tongliang with us. So Tongliang will share with us some ideas regarding how to handle label noise. So before the presentation, let me just quickly say something about Tongliang. So Tongliang is the director of the Sydney AI Center at the University of Sydney. He is broadly interested in the fields of trustworthy machine learning and its applications across many disciplines, and with a particular emphasis on learning with label noise, noisy labels, adversarial learning, transfer learning, unsupervised learning, and statistical deep learning theory. Basically, he was also expert in learning theory. He has been AC for many top conferences in machine learning, including ICML, NeurIPS, ICLR, UAI, AAAI, IJCAI, and KDD. And he also received the Discovery Early Career Researcher Award from Australian Research Council, and was named in the Early Achievers Leaderboard of Engineering and Computer Science by the Australian in 2020. So it's really nice to have you here. Basically, I know you are the expert in wiki super learning, and recently you also have been interested in not only just trustworthy machine learning, but also how to leverage the causal principles in solving those problems. So whenever you're ready, please, Tongliang.
Yeah, thank you very much, Quinn, for the very nice introduction. Okay, let me share the screen. I suppose you can see the screen now. Okay, let's start it. So I'm also the director of the Trustworthy Machine Learning Lab. So first of all, I'd like to promote the trustworthy machine learning. We know that now, nowadays, the machine learning or artificial intelligence tools and algorithms have been widely used. Almost everyone use smartphones, so we use the machine learning algorithms and tools. For example, buy air tickets, book a hotel, and even shop online. And we do a lot of activities daily. So are you worrying that your personal information will be abused by the others? Or are you worrying that the decisions to you, especially when you are from a minority group, is not fair? Okay, so there's a lot of concerns when we use the machine learning algorithms and tools. So trustworthiness is very important. It has many interpretations. For example, a trustworthy machine learning algorithm should be explainable, should be robust, fair, causally responsible, privacy preserving, etc. A lot of others. So trustworthiness, I think, is the foundation for our society to widely deploy machine learning or artificial intelligence tools and algorithms. That's why we founded the Trustworthy Machine Learning Lab in 2020, and we also attracted a lot of talents joined our lab. And on today, we would like to focus on a very specific subtopic of trustworthiness, which is algorithmic robustness. So what is algorithmic robustness? We know that for machine learning algorithms, it has input and output. Okay, when the input, for example, the input training data is of low quality, generally the output, for example, a classifier, will also have a low quality. However, sometimes when the input is of low quality, we expect that the output still have a good property, right? A good quality. So if an algorithm has such a kind of property, then we call the algorithm is robust. And today we will focus on a specific low quality of data, which is label noise. So I assume that many of you don't know what is label noise and why it is important. How can we deal with them? Now today, I would like to roughly introduce you the story and hope that you will get the idea how to deal with label noise if you met similar problems. So why label noise? Now we are in the era of big data. So we use a lot of large models, deep neural networks. Okay, we need a lot of data, training data to train those large models. Many of them are supervised learning method when we train the models. So we need a very large data set, supervised data set. Usually, when we accurately label the large-scale data set, it will take a lot of laborers, time, and expert. So we need a lot of expert and spend a long time to carefully annotate those large-scale data set. It is also very costly, right? To avoid those, some cheap methods have been proposed to label the large-scale data set. One popular one is crowdsourcing labeling. Okay, so we have very large-scale data set, and we divide it into small subsets. For example, for each small set, it contains several hundred, for example, of images, and we distribute those subsets online and ask someone to label them, and we pay those annotators. So this is called crowdsourcing labeling. One very famous platform is Amazon Mechanic Turk. So it's a commercialized platform. So a lot of non-expert, they can use this platform to earn money by labeling some data. So obviously, those annotators, sometimes they want to earn as much money as possible. So they may, for example, just quickly click some labels. So the label quality may be low. So they must contain some label errors. So when a data set contains label errors, we see that it contains label noise. There's many other reasons which will cause label noise. We just summarize 3 here. The first one is that now to label large-scale data sets, many of the labelers are non-expert. They are non-expert, then the quality cannot be guaranteed. The second reason is that the labeling task itself is subjective. Okay, for example, for some disease, even some very experienced doctors, they may have some different opinions. They can provide different labels because it is a very subjective task. The last reason is that for many data, the data itself contains insufficient discriminative information. For example, given an image, the image, for example, is very blurred, and it is very hard for us to identify the content. Then when we label the image with high probability, we will make mistakes. So label noise now is ubiquitous. It's a common problem. So are label noise harmful, and why we need to care with label noise? So I show you the figures here. These figures are cited from this ICLR paper in 2017. And this paper won the Best Paper Award, a very excellent paper. So they show that for the training procedure, even we random flip the labels, which means that the relationship between the instance and the labels now are randomized. So the training error, the training loss will reach 0 if we keep training the model, because the model is very large. They can overfit the relationship between X and Y. However, when we test the model, here for the figure on the right-hand side, the horizontal axis represents the label corruption. For example, 0.6 here means that 60% of the labels are wrong, okay, for the test data. And for the vertical axis, it represents the test error. We can see that when we increase the label errors, the test error will also increase, which means that the training error is very small, reach 0, but the test error is very large. Sorry, this is the overfitting problem, right? So which means that if we have label noise, the large models will overfit the training data and cannot generalize very well. So this is harmful. So when we employ the model and we do the test, the performance will not be good. Also, we know that for many large models, they are non-convex. For example, if we train a deep model, okay, we will train many epochs. A lot of models will be generated during the training procedure. And we need to select a proper model for test, for deployment. So which model should we choose? This is also a traditional machine learning problem. Normally, we use a validation set to choose the model, okay? But we assume that the training set, the validation set, and the test set, they have the same distribution. So if a model works very well on the validation set, we assume that it can also work well on the test set. However, for label noise problem, the validation set also contains label errors. So when we choose a model by using the validation set, obviously it will be suboptimal because the errors, label errors will have some side effect. So for the training, both the training procedure and the model validation procedure, label noise is harmful. We need to carefully deal with label noise. Just now, you may have the feeling that label noise is a problem for large-scale data set, should be the problem for industry, right? However, even for the data set in academia, we found that they also contain a lot of errors. So some colleagues from MIT, they just relabeled the test set or validation set of 10 popular data sets from computer vision, natural language processing, and the audio data set. And here we present several very popular ones. For example, SAFA, IMINET. I assume that you should be very familiar with those data sets. And for those 10 popular data sets, on average, 3.4% of the labels in test set or validation set are wrong. Okay, and specifically for this IMINET data set, 6% of labels in the validation set are wrong. Okay, as said, usually we assume that the training data and the validation data, they have the same distribution. And we can assume that in the training data set of ImageNet, there is also 6% labels are wrong. And for those 10 popular data sets, on average, 3.4% of labels are wrong. So we should also carefully consider the label errors. For example, here I show the leaderboard of the ImageNet. Okay, here, this is the top one accuracy. We can see that in this year, 2022, the best models, they have top one accuracy above 90%. Okay, and just now we introduced that on the training data set and the validation set data set, they have 6% of labels are wrong. However, all those models, they haven't considered this. If we consider label errors or label noise, we believe that the best models should be different. Okay, should be different. There's also a lot of room for improvement. And now I would also like to introduce you some more applications, very interesting applications about learning with noise labels. Now, one term is very popular, which is data-centric AI, which means that when we have very good data set, we can train very good models. Okay, which this also implies that data set is very important. Is very important for the development of artificial intelligence. So many giant companies, big companies, they want to create data set. So during the creation, one important task is to label or annotate those large-scale data sets. So the company, they want to spend less money to obtain high-quality labels. Okay, for example, if we use crowdsourcing labeling, so the annotators, they want to earn a lot of money, but they want to pay less effort. If they pay less effort, this implies that the label quality would be low. So there's a game between the company and the annotators if we want to build a system to optimize the interest of the of both the company and the annotators. I think this is a very important application for constructing data set. So our research will help measure the quality of labels, especially only given the noisy data, and how can we measure the quality of the labels. Okay, this is also a key step to play this game. And after the talk, you will have a rough idea how to measure the quality by only exploiting the noisy labels. Okay, I would like to make a quick summary here. We just discussed that label noise is ubiquitous now in the era of big data, and also it is very harmful. It will, during the training procedure, it will cause the overfitting problem. And also during the model selection procedure, it will cause the suboptimal problem. And also dealing with noisy labels, we have a lot of real world applications, very interesting applications. And now we have the problem, how to deal with label noise. Okay, we start by introducing the setting. Okay, what we have and what we want to obtain. What we have is a noisy training sample, and here we denote this by S tilde. Okay, tilde here denotes the noisy data, and we have X and Y. Usually we call X as the instance and Y the labels. Y tilde represents that the label is noisy. Noisy does not mean that it is wrong. So noisy means that it could be correct, the label could be correct, and it could be incorrect, but we don't know. Okay, so we have n training examples. The pair XY is called a training example. So for the n training examples, some of the labels are correct and some of the labels are incorrect. And those n training examples will make up a training sample, which is the noisy training sample. This is what we have. And we want to, what we want to obtain is, for example, a classifier. Or we want to learn how many labels are wrong, incorrect. Okay, so what is the classifier we want to learn? We should define the classifier. Okay, usually the best classifier in statistical machine learning is a Bayes classifier. It is defined by using the class posterior. This probability P of Y given X is called the class posterior. And we can define the Bayes classifier by using this class posterior. It means that given an instance, which label will achieve the largest probability, and then we assign this label to this instance. Okay, this is a Bayes classifier. We have a noisy training sample. We don't have clean labels, and we want to learn a Bayes classifier defined by using clean data, clean labels. So this task is challenging. Nowadays, there are two major categories of methodologies to deal with label noise, to learn a good classifier. The first one is to extract confident examples. So what is confident examples? Confident examples are those examples whose labels are more likely to be correct. So if we just use those data with correct labels and discard those labels which could be wrong, then the side effect of label noise could be reduced. Okay, a lot of methods have been proposed in those categories, and they do have good empirical performance. Another category focuses on label noise learning. So the term, you can see that label noise learning, we are going to learn the label noise. We want to study the properties of the label noise. If we know the noise very well, for example, we model the label noise, and we can better handle it. So for the second category, many statistically consistent algorithms have been designed. So what is statistically consistent algorithms? Those algorithms if the training algorithms will statistically converge to the base optimal classifier. If they satisfy such a property, those methods will be statistically consistent. And we will give you more details later. First of all, I would like to intuitively introduce how can we extract confident examples. Okay, we use small loss tricks, or it is also a term which is called early stopping. And we can explain this by looking at this figure. So this is also obtained by doing an experiment. For this vertical axis, it represents the training accuracy. Okay, for the horizontal one, it represents the training epochs. For the right curves, we have two right curves, a solid one and a dashed one. For the right curves, it represents that 20% of the training data, the labels are incorrect. And for the orange ones, it represents 40% of the labels are incorrect. And for the solid ones, it represents the training accuracy of the data whose labels are correct. For the dashed ones, it represents the training accuracy of the data whose labels are incorrect. Now we can see some interesting phenomena. In the early stage, during the training accuracies of the data with correct labels are very high, while the training accuracy for the data with incorrect labels is very high, it is very low. So they have different phenomena. So if we stop training, for example, at the 50 epochs, which means that the model is trained mainly by exporting or fitting the data with correct labels. And if we keep training the model, then finally the model will fit the data with incorrect labels. So early stopping can be used for dealing with noisy labels. So because the deep networks will usually fit the clean data. And this is also called the memorization effect of deep networks. Okay, deep networks will first fit the majority of data, the patterns, and then the minority of the patterns. So for dealing with label noise, we usually assume that the majority of the labels are correct, the minority of them are incorrect. So this, because the semantic of labels is endorsed by humans. So if the majority of people call a dog as a cat, after a while, dog will become cat. Okay, so if you have any questions, please feel very free to interrupt. I can see there's some message in the chat box.
Actually, there's a message. Sorry, there's a question. In case you can take a break right now, maybe you can answer it. Maybe you can read it, or I can just read it for you.
I can read it now. So the question is how about the noisy labels for regression problem? Okay, this is a very good question. So on today's talk, we only focus on the classification problem. So what's the difference between classification and regression? For classification, the target Y is discrete. For regression, it is continuous. So label noise is only defined for the discrete problem. Of course, the ideas may be applied for the regression problem, but we do not discuss it here. Okay, thank you. So as discussed, by looking at this figure, so this is just an empirical observation. The deep networks will first feed the majority of the data, the clean labels, and then the noisy labels. So if the model feed the data with clean labels, then fx will be very close to y tilde, which means y tilde is a clean label. Then the loss itself will become small. If y tilde is a noisy, incorrect label, at the early stage, f of x is far away from y tilde. The corresponding loss will be large. So we can use the value of the loss to extract confident examples, right? Because for the data with correct labels, it will be firstly fitted and the corresponding loss will become small. So the small loss trick and early stopping method have been used to heuristically extract confident examples.
Oh, here, Tongliang, sorry to interrupt you, but there was a question. So relevant to the previous slide. In the plot, are you referring to symmetric or asymmetric noise?
Okay, yes, this is a very detailed question. It shows that the colleague know a lot of knowledge in dealing with noise labels. That's great. So that is for symmetric label noise. Thank you. And yes, we would like to make a quick summary here so that you can better understand the talk. So we have discussed that to deal with noisy labels, there are two major categories. The first one is to extract confident examples. We just roughly introduce you the idea. And another category is to model label noise. So in the rest of the talk, we will focus on the second category, model label noise. To model label noise, we have to know how label noise will be generated. So we have two models for generating label noise. The first one is that we assume the noisy class conditional is a combination of the clean class conditional. So P of X given Y is called class conditional. So this is just an assumption. We assume that those probabilities satisfy those equation. Okay, and in a different way, we can also assume that the noisy class posterior is a combination of the clean class posterior. They satisfy such a probability. Okay, on this talk, we will focus on the second assumption. Okay, we assume that the noisy class posterior is a combination of the clean class posterior. We can give you more details. So here, the second equation is obtained by using the law of the total probability. Okay, the right-hand side can be obtained by introducing the latent variable clean variable y. Okay, we can see that by comparing those two equations, we can see that beta has a good interpretation. Sorry, it equals this probability. It means the probability that given an instance is clean label is I, but what we have observed the noisy label is J. So the clean label flipped to the noisy label J. So beta represents this probability. Beta describes the relationship between the clean label and the noisy label. So beta is very useful. And now we can have this equation. Basically, this equation. This is a vector formed of the law of the total probabilities. For example, the first entry of the noisy class posterior equals the first row of the column dot producted by the clean class posterior. So this is the law of the total probability. Okay. So the noisy class posterior on the left-hand side, we assume that it can be obtained because we have the noisy training sample as we discussed as third. If we design a calibrated model, we can have a good estimation for this noisy class posterior. Our aim is to learn the clean class posterior. As I said, it can be used to define the Bayes classifier. So if we know the matrix in the red box, the clean class posterior can be inferred because we know the noisy class posterior. Given the matrix in the box, the clean class posterior can be inferred. So the problem now remains how to learn the matrix. We define the matrix as a label noise transition matrix. This is a very complicated matrix. It is a matrix valued function for different instances. The matrices are different. It is very complicated. So for doing research, we can start from the easy problems. So we assume that the transition matrix can be instance independent. Okay, for example, if an annotator just randomly clips the labels, the label error is instance independent. And for some situation, if the instance in each class is well clustered, then we can also use this instance independent transition matrix to approximate the instance dependent transition matrix. Okay, we just focus on the instance independent transition matrix, and we recall the setting, how to learn the transition matrix, the instance independent transition matrix. Just now we can just focus on the binary classification problem. Okay, let's look back to the setting. We know that for the transition matrix, the summation of the column will equal 1. Okay, you can say the summation of the column equal 1. For binary classification problem, the matrix is a 2 by 2 matrix, and if the column, each column, the summation of each column equals 1, then we only have 2 variables for a binary classification problem. Okay, we denote them as t plus 1 minus 1. It represents that the clean label is -1, while it flips into a +1 label. Okay, similarly, t minus 1 plus 1 represents that the clean label is +1, but we observed the noise label as -1. Okay, the transition matrix built a relationship between the noisy class posterior and the clean class posterior. So the 2 equations, by some easy arrangement, you can easily obtain those 2 equations. And here we just show you some interesting observations. And we can see that just now we assume that the majority of the labels are correct and the only minority of them are incorrect. So those 2 factors are both less than 0.5. So the factors 1 minus t plus 1 minus 1 minus t minus 1 plus 1, this factor is a positive number. We also know that the probability are non-negative. Okay, so the probabilities, the noisy class posteriors on the left-hand side will be always bigger than or equal to t minus 1 plus 1. This is a very nice observation. If the equation can be reached, then we can use the left-hand side to estimate the entries of the transition matrix. So we have the question, can we reach the equation? The answer is obvious. When the probability in the red box equals 0, then the left-hand side, we can use the left-hand side to estimate the entries of the transition matrix. Okay, so we just assume that the training data contains some instance will make this clean class posterior reach 0. Then we can design an estimator just to estimate the transition matrix. Okay, this is the for the binary classification problem. Okay, if we assume that the training data, now I would like also to introduce you the concept of anchor point. So it's defined in the clean data domain. So if, for example, xi is called the anchor point of the S class, if it belongs to the S class with probability 1 and probability 0 to other classes. So just now, we said that when this probability reaches 0, we can use the left-hand side to estimate the entries. So when it will reach 0, we need to introduce the concept of anchor point. Okay. So when the training data contains anchor point, we can also use this estimator to locate the anchor point. When we locate the anchor point, we put this anchor point into the noisy class posteriors, we can obtain the entries, an estimation of the entries of transition matrix. Okay, this is somehow abstract, but if we introduce you the multi-class classification problem, the idea will be clear. For example, now we introduce you the anchor point of the first class. Okay, as discussed, it is defined in the clean class domain. So the clean class posterior is the 1 hot vector. So the left-hand side equals to the first column of the transition matrix. If we want to estimate the ith column of the transition matrix, we can just use the anchor point from the ith class. Okay, such an estimator is called T-estimator, which can be used to estimate the instance independent transition matrix. Okay, the T-estimator, it use anchor point. We assume that there exists anchor point. So such assumption is strong, right? So we may ask, do we really need the anchor point assumption? Can we use some weaker assumptions? The answer is positive. So here we will introduce you a weaker assumption, and it is a bit complicated. We just introduced you the intuition here, and also to introduce the intuition, we need some definitions. The first one is a convex combination. So we have n vectors. A convex combination of those n vectors is defined by this way. So for each alpha, it is non-negative, and the summation of alpha equals 1. Also, we want to introduce you the concept of convex Hall. So all the collection of the convex combinated point will consist the convex Hall. Okay, and the concept of extreme Ray point. So if x1, x2, and xn, they are linearly independent, then they will be the extreme Ray or extreme point of this convex Hall. So those definitions are quite abstract, but why we want to introduce it? Because we can see that the definitions will be closely related to the equation here. We can see that for those noisy class posteriors, they can be written in this way. For example, for the first entry, it is a dot product of the first row with the clean class posterior, and we can say that it is dot product the clean class posterior the first of the first row. So we can see that each column of the transition matrix, they are linearly independent because the diagonal entries are the large values than the off diagonal entries, because we assume that the majority of the labels are correct. So the diagonal entries are the largest values. Those columns will be linearly independent. Okay, so the noisy class posteriors will make up the convex Hall. Okay, and the corresponding extreme Ray or extreme point will be the column of the transition matrix. So this is a very nice interpretation by using the definitions we introduced before. And we can see that for the anchor point assumption, when we estimate the transition matrix, we use the anchor point assumption. Okay, it is when we use the anchor point assumption, we can identify each column of the transition matrix. Okay, as discussed, for each column, it is the extreme Ray of the convex Hall. If we normalize the convex Hall, we can, for the 3-class classification problem, the convex Hall can be represented by the right triangle here. So in order to find or identify the transition matrix, okay, we can just identify the extreme Ray here. So when we use anchor point, we can identify the extreme Ray. But we have the question, if we want to identify the extreme Ray, do we really need the anchor point? Okay, the answer is negative. So when we want to identify this right triangle, we may just identify, for example, the edge. Okay. When we identify 3 edges, we can also identify this normalized convex Hall. So we summarize the properties to identify the edges by introducing a new assumption, which is a sufficiently scattered assumption. When we have such assumption, the right triangle can be identified by the triangle which have the minimum volume, which includes all the noisy class posteriors. Okay, this can be proved. So with such an assumption and such a proof, we introduced a new network to learn the transition matrix and the classifier at the same time. Okay, so we minimize the volume of the convex hull consisted by the transition matrix. Okay, we can learn the transition matrix and the classifier. And we can also prove that the transition matrix we learned here will converge to the optimal one, and the classifier also converge to the Bayes classifier. Here we show you some examples showing the reconstruction error of the transition matrix. We can show you that the reconstruction error of this blue line, the volume mean network, will works better than the baselines. Okay, for all the majority of the baselines, those methods are also proposed in our group. We also would like to make a quick summary here. How to identify the transition matrix and how to estimate the transition matrix. We introduce you the T estimator, which use anchor point assumption. So the anchor point assumption may be strong, then we introduce you the sufficiently scattered assumption, and correspondingly, we propose the volume mean network to learn the transition matrix and the classifier at the same time by an end-to-end way. And here we also want to quickly introduce you.
Sorry to interrupt you. Sorry, yes. I have to interrupt you, Tongliang. So there's another question in the chat box relevant to this part. How stable is that?
How stable? Yes, this is a very good question. So normally, when we estimate the noisy class posterior, the estimation error is large. Okay, so if we just focus on the estimation of the noisy class posterior, so it has a large estimation error. We have a different work to deal with this problem, which is called DOT method. So if you are interested, please contact me later. So that method, for that DOT method, when we estimate the transition matrix, we avoid directly estimating the noisy class posterior. So the large estimation error can be avoided. So let me finish reading the question. How stable is estimation of the true posterior from noisy posterior with respect to X-dependent perturbations of the transition matrices? We use single transition matrix for all X, but we know that it varies from different ones. Okay, I think this problem is more about why we use the instance independent transition matrix rather than these instance dependent ones. Okay, just now we said that we can use the independent ones to approximate the dependent ones. But from now on, I will also introduce you how to estimate instance dependent transition matrix. Yes, you are right. For different instances, the label patterns may be different. For example, an image, if that is very blurred, then it may have a higher rate to have label noise. Okay, I will quickly introduce you how to estimate instance dependent transition matrix here. The setting is the same. Okay, the first method is that the method is inspired by sparse coding or dictionary learning. So there is some evidence showing that we humans perceiving instance by decomposing them into parts. So this work was published in Nature or Science in early 20,000. So for example, they're showing that for many instances, okay, of faces, they share some common patterns. For example, those patterns can be obtained by using non-negative matrix factorization. Okay, those bases, we call them as patterns. For different human faces, they can be reconstructed by using the same basis. And inspired by this, we assume that for those different patterns, they have fixed label noise patterns. For example, for W1, this basis For example, it has a pattern of I's, and we assume that it has a fixed label noise transition matrix, instance independent ones. And for different bases, we have different patterns. Similarly, we know that for an instance, we should have instance dependent transition matrix, right? So we assume that the instance dependent transition matrix will be combined or reconstructed by using this fixed basis dependent transition matrix. Okay, for example, for each human face, it can be reconstructed by using this basis. And we also assume that for each instance dependent transition matrix, it can be combined by using those fixed transition matrices. So those fixed transition matrices can be learned by using the, for example, the anchor point assumption or the sufficiently scattered assumption. We can obtain them. But the question is how to obtain the combination parameters. Those combination parameters should be different. Okay. Similarly, for when we reconstruct an image, a face, the construction parameters should be different. Okay. But how can we learn those parameters? This is a hard problem. So we just assume that those two reconstruction procedures, they share the same parameters. So when we reconstruct a face, the parameters can be optimized. So we just reuse these parameters to reconstruct this instance dependent transition matrix. It works quite well. Okay. And also, I would like to quickly introduce you the last piece of work, which we use a parameterized way to learn the matrix valued transition matrix. Okay, it contains three variables, x, y tilde, and the clean y. However, we don't have any observations of the clean y. So it is difficult for us to directly learn this matrix valued function. Okay, so how to solve this problem? At the very beginning, we introduce you the method of extracting confident examples which have correct labels, right? So we just use those methods to extract some confident examples. We assume that their labels are correct. And also we did some analysis showing that for some cases, those confident examples, their labels can be proved that they are correct. And if, especially for the low label noise rate settings. For example, for the noise, here I give you an example. We have the noisy class posterior. Okay, the second entry is the largest one. But the clean labels is defined by the clean class posterior, right? We don't know the clean class posterior. But if we know that the label noise rate is very small, assume that the label noise rate is 0, then the clean class posterior should be the same as the noisy class posterior. But if the label noise rate is very small, the second entry should be of the clean class posterior should be some value around 0.85, right? So we know that it is bigger than 0.5. So the Bayes label, which is assigned by the Bayes classifier, should be the second class. So, which means that by only giving the noisy class posterior, for some examples, we can identify the Bayes labels. We have Bayes labels, we have noisy labels, we have instance, so we can use a parameterized way to learn this Bayes label transition matrix. It also works very well, and this work was published in ICML this year. Lastly, we want to call for the reconstruction of data set. As we said, the data set is very important. We have different ways to generate label noise. For example, using crowdsourcing labeling, use transfer learning, or we just search some data, some images or some data from search engine, and those different methods, we assume that there are different label noise, different kind of label noise. And here we just release the data set. We relabeled the CIFAR data set by using crowdsourcing labeling. For those CIFAR and data set, we have the clean labels, we have the noise labels. So it is very easy for us to learn the patterns or the properties of label noise. So we call for many other data sets which contain both the clean labels and the noise labels, so that we can learn the properties of label noise better. So we quickly make a summary here. To learn instance-dependent transition metrics, firstly, we introduce you the path-dependent transition metrics. We assume that the label noise, it depends on different paths. And then we use a parameterized way to learn the metrics value, the transition metrics. And lastly, we call for some real-world data set with both clean labels and noisy labels. We did a lot of work on label noise. So on today, we just introduced you a part of them. If you are interested in label noise, we will have a book published by MIT in 2024. So if you are interested, please read this book. So I would like to make the conclusion and give you some discussions about future work. I would like to say that learning with noisy labels is at the early stage. There's also a lot of opportunities. So learning with noisy labels is a fundamental problem because classification is a fundamental machine learning problem. Okay, we have done a lot of work by modeling label noise. Okay, so we introduce you some of them. All those work only exploit the noisy data. As said, when we just exploit the noisy data, we can use those methods to measure the quality of the data provided by annotators. Okay, so in the future, I think it is also very important to connect different noise, for example, the feature noise, especially the adversarial noise with label noise, so we can handle the real world problem. And also in the future, we want to build systems to optimize the interest of both companies and the annotators. As discussed, there is a game between the companies and the annotators when we, for example, use crowdsourcing labeling to label large-scale data set. Thank you. That's my talk. If you have any questions, please feel very free to ask.
Cool. Thank you very much, Tongliang. It's a great talk. So let's see whether we have questions from the audience. So you can just raise your hand or you can just post your questions in the chat box.
Yes, just now I introduced several work, but actually I mainly introduced the intuitions. So you don't need to get the details, but if you have any questions about the intuition, the high-level logic, please feel very free to ask.
While we are waiting, I guess some of them are writing questions. So as a follow-up to what you just said, right? Let's try to make the intuition. Maybe we can just talk about the intuition once again. So essentially, without any further assumptions, like smoothness of the classifier or classification boundary, right, or particular properties of the transition matrix, we cannot solve the problem, right? So can you,
yes.
Clearly different kinds of assumptions would be useful, right? So could you just give a recap on all those assumptions on which the problem becomes well posed so that you can really recover the truth?
Thanks, Quinn, for the very insightful question. Yes, indeed, for the problem, if we only have the noisy training data, to learn the classifier and the transition matrix is an ill-posed problem. So just now we have introduced the several methods. For example, to learn the class-dependent, instance-independent transition matrix, we introduce you the anchor point assumption, the sufficiently scattered assumption. All those assumptions are proposed to ensure that the transition matrix can be identified. For the real-world problem, if the assumptions cannot be satisfied, then the transition matrix cannot be identified. For the class-dependent, instance-independent problem, the identification of the transition matrix could be easier. However, for the instance-dependent problem, how to identify the transition matrix, the matrix valued function is a very interesting problem. we introduce you two work in this category. The first one is the part-dependent transition matrix. Okay, for that problem, we also have a assumption. We assume that the label patterns depends on the basis of the instance, based on the part of the instance. For each part, it is fixed. So for this problem, if we further assume that for each part there exists anchor point, then the transition matrix can be identified. However, for the second method we have introduced, which is a parameterized method, for that problem, the identification, now we cannot provide you any identification. That is a very hard problem. As a conclusion, I can say that for many of the problems, identification is very hard. So, but that is a really interesting problem. We try to solve this problem. That's why we also call for real-world data set. So we want to explore more specific properties of label patterns, and in the hope that by using those properties, we can better identify the label patterns.
Great, thank you very much. So essentially, as you just mentioned, identifiability is really a big problem if you really want to provide the guarantees. And at the same time, you want to make sure that the assumptions are testable so that users can really understand what's going on in the result. And regarding even in the last situation where you have say feature dependent, right, transition matrix, we also with Tongliang Liu, we also tried to do something essentially under some assumptions related to the latent class model, and then you can just establish identifiability. So by that I mean this is I would say this is really a very important and emerging direction, and in the future quite some identifiability results can be established to provide guarantees. But thank you very much for the summary. Now let's just take questions. So first one is from Kevin Wu. How can you distinguish between hard label and noisy label? Asymmetric label.
This is a very good question. So this is also the hard question: how to distinguish between the hard ones and the noisy one. Usually, the hard labels is entangled with the noisy labels. It is very hard. So, but as discussed, we can design, with some assumptions, we can design statistically consistent algorithms. So which means that if we have sufficiently large data set, the classifier is optimal, and the labels assigned by the classifier will be optimal, and the hard labels and noisy labels can be distinguished. But this is the ideal case. For the real world problems, it is very hard, and we don't have any very convincing method yet. But this is also a research direction, how to propose some interesting method to distinguish the two.
Wonderful. And also that's why you have to assume something, right? Without assumption, you cannot really provide guarantees. Cool.
That's
and
true.
We have a question from Asma Hashmi. So is the transition matrix learned jointly with the classifier?
Yes, this is also a very good question. So for some of the methods, for example, the T estimator, we need to firstly identify the anchor point and then learn the class posterior. And we use a noisy class posterior. We use a noisy class posterior of the anchor point to estimate the transition matrix. So this is not end-to-end method. It involves several stages. And for some methods, for example, the volume mean network, for that method, we learn the transition matrix and the classifier jointly in an end-to-end way. Okay, so for different methodologies, they are different. I hope I answered the question.
Wonderful. Let's take next one. So it's from Yasser Daho. How is the transition matrix optimal sensitive to the optimizer at hand, like SGD versus Adam? And the learning rates models usually fit noise levels after LR drop. So that is a very, very practical issue.
Yeah. So this is a very interesting problem. We did some experiment. So generally, if I want to answer this question, I would say that it should not be very sensitive, because, for example, if we have assumptions, as discussed, if we have assumptions, many of the estimators are unbiased. Theoretically, different method use different optimization method, we can still obtain a good result. However, for real world problem, when the data set is finite, so we do have the problem. So we propose a method which is called a T-revision. When there's no anchor point, we use T-revision to solve the problem. For that method, it is quite sensitive to the optimizer. At the early stage and later stage, we use different optimization method. So for that method, it is a bit sensitive, because for that method, it is heuristic and don't have theoretical guarantees. So for this question, I just give you some of my personal opinions, and those opinions are based on the experiment. So this is a very good question. So I cannot give you very concluded answer. Sorry for that.
That's great. So actually, probably you can have some discussion offline, especially if you are faced with this kind of real problems, right? You can have email exchange. Wonderful. So, and next one from Asma Hashmi. How is the model performing when the pair flip noise gets increased to 50% or even above?
Okay, so here we have a specific term here, pair flip noise. Okay, if we don't have such a restriction for the general label noise problem, even the rate is above 50%, we can still handle them, because the class number could be large. If, for example, if we have 10 classification problem, even when the noise rate is above 80%, still for the noisy data, majority of them are clean for each class. So we can still easily handle them. Okay, but for the pairwise flip problem, this is a very hard case, because only one labels from one category will flip into another. Two of them will flip. So this is a very challenging problem. So currently for the most of the experiment we have done, the rate is below 50%, and they perform quite well. I assume that even the label noise rate is above 50%, we can still have some good performance, but the performance drop could be large. So I don't have any specific observation, but that is my expectation. Thank you.
Wonderful, thank you. And next question is from our Tim Baldwin. Tongliang, probably you know him. Okay, so your work assumes pre-labeled data, but in the interactive case where there's a fixed labeling budget and the possibility of active learning, known as intense selection for redundant labeling of hard instances, how would you modify your approach to address this scenario?
Yeah, thanks, Tim, for the very interesting problem. Actually, we have thought this before. And even at the beginning, we have the discussion, do we really need active learning when we have a very large scale data set? Because we have a lot of very interesting observations. For example, the method which just extracting confident examples. And those examples, intuitively, they should be biased, right? Because by certain criterion, we just extract those confident examples. But the results showing that even we just focus on those extracted confident examples, we can still obtain very good performance. So this implies that for a very large data set, we just use a cheap method to label them, and then we quickly extract confident examples, we can obtain a good result. So active learning is a powerful method, but usually when we actively label some instance, we need some expert, right? If those carefully selected examples are mislabeled, then it will be very harmful. So active learning could be somehow expensive. So we have the discussion if we really need active learning. But I do believe that active learning is very useful. But currently, in the community of learning with noisy labels, very few work have considered combining active learning to deal with the problem. So how to modify your approach? I think this should be a very promising direction. Yeah, and of course we can combine a lot of very powerful tricks in the community of active learning, but we haven't done any experiment. But I agree with you that this is a very promising direction.
This is very interesting, right? Because if the levels obtained by active learning are actually wrong, right? The consequence would be kind of huge, right? So you clearly have to modify your approach to deal with such scenarios. Wonderful. Thank you. So if you have a follow-up question, please just put them here. And the next one is from Asma Hashmi. Do you think the learning of transition matrix would become better if we understand the causation behind the noisy levels?
Yeah, this is a very great question. And actually, we also did some work here, collaborated with Quinn. So it is really helpful. And also I can give you another example. So we have introduced you two categories of methodologies. One is extracting confident examples, and another one is to model label noise. And there's an argument which category works better for the real world problem. And for the first category, we can extract confident examples. For the non-confident examples, we can just discard the labels and using the semi-supervised learning method to learn the classifier. For many image data sets, those methods achieve the state-of-the-art performance. So they are arguing that those methods works better, and it is not necessary to design transition matrix method. But we argue that if we know the concession behind the data generalization procedure, if X is a cause of Y, so if X is a cause of Y, then many of the semi-supervised method is not useful, right, to learn the classifier. In this way, however, if we use transition matrix-based method, we can still make use all of the data set and design statistically consistent method. So I just answer you that if we know the causation, we can do a lot of things here.
Wonderful. Oh, thank you very much. So is there any other questions? Actually, we are running late. So if there are no other questions, thank you very much. So thank you very much for our audience, to our colleagues for the wonderful questions. Thanks very much, Tongliang, for your wonderful presentation and the answer to the questions. Thank you very much.
Thank you, everyone. It's my pleasure.